Somewhere inside a quantum computer right now, a qubit is failing. Not dramatically, not with some flashing warning light, just quietly losing its delicate quantum state, the way a whisper gets swallowed by wind. For years, fixing that failure meant throwing armies of physicists and painfully slow classical algorithms at the problem, hoping they could catch the error before it wrecked the entire calculation. Nvidia just handed that job to an AI, and in doing so, they may have just redrawn the blueprint for what a quantum computer actually is. Here's the sentence that should stop you mid-scroll. Nvidia doesn't build quantum computers. It never has. It builds graphics processing units, the same chips that render video games and train chatbots. And yet, in 2026, Nvidia quietly became one of the most important companies in the entire quantum computing industry. Not by building a single qubit, but by teaching artificial intelligence to fix the one problem that's kept quantum computers from actually working. It's a strange kind of quiet too, because this isn't a company known for staying out of the spotlight. Nvidia has spent the last several years becoming one of the most talked about, most valuable companies on the planet, driven almost entirely by its role powering the artificial intelligence boom. So it's genuinely surprising that one of its most significant recent moves, quietly repositioning itself at the center of an entirely different, equally transformative technology, has generated so little mainstream attention by comparison. To understand why this matters, you first have to understand the ugly secret sitting underneath every quantum computing headline you've ever read. Qubits are broken almost constantly. Not occasionally, not rarely, constantly, in ways that rarely make IT into the glossy press releases companies put out. The tiniest vibration, a stray bit of heat, a whisper of electromagnetic interference, any of it can corrupt the fragile quantum state to qubit is holding in a fraction of a second. This is quantum computing's original sin, and for decades, the entire industry has been racing to solve it, because until it's solved, quantum computers remain fascinating laboratory curiosities, instead of tools anyone can actually rely on. The solution scientists came up with is called quantum error correction, and the basic idea is simple, even if the execution is brutally hard. Instead of trusting one fragile qubit to hold a piece of information, you spread that information across many physical qubits working together, creating something called a logical qubit. If one of those physical qubits fails, the system can detect the error and correct it without losing the underlying information. Think of it like writing an important sentence in pencil, then having a dozen friends standing around watching, ready to instantly notice and fix even a single letter if it starts to smudge. That analogy actually undersells how demanding this problem really is once you consider the scale involved. A single logical qubit, the kind stable enough to actually be useful for a real calculation, might require dozens or even hundreds of individual physical qubits working together just to protect it from noise. Multiply that by the thousands or millions of logical qubits a genuinely powerful, world-changing quantum computer would eventually need. And you start to see why error correction isn't just one engineering challenge among many. It's arguably the single largest bottleneck standing between quantum computing as it exists today and quantum computing as it's been promised for decades in headlines and keynote presentations. But here's where it gets brutally difficult. Detecting and fixing those errors has to happen in real time, faster than the qubits themselves can decay, which means the system has almost no time to figure out what went wrong and correct it. We're talking about decisions that need to be made in millionths of a second over and over again, continuously, for every single qubit in the system all at once. Traditional decoding algorithms running on traditional processors simply can't keep up once a quantum computer scales beyond a relatively small number of qubits. It's a bit like trying to catch 1,000 balls thrown at you simultaneously, using only your own two hands, and somehow doing it perfectly, forever, without dropping a single one. For years, researchers dealt with this bottleneck using classical decoding. Algorithms, mathematical methods that work reasonably well on small systems, but start to buckle under their own complexity as the qubit count climbs. One of the most widely used classical approaches, a method called minimum weight perfect matching, has served as something like the industry's baseline standard for years, reliable enough to get the job done on modest-sized systems, but increasingly strained as researchers push toward the kind of scale genuinely useful quantum computing will eventually demand. It's the kind of tool that works fine until the exact moment you actually need it to work at scale, and then it quietly becomes the thing holding everything else back. This is exactly the wall Nvidia decided to attack, not by building better qubits, but by building smarter software to watch over the qubits other companies are already building. In April 2026, the company released a family of AI models called Ising, named after a foundational concept in physics, specifically designed to handle two of the thorniest problems in quantum computing, calibration and error correction decoding. Let's break those two problems down separately, because they're both fascinating in their own right. Calibration is essentially the process of constantly tuning a quantum processor so its qubits behave the way they're supposed to. Historically, this work has been done by human physicists manually adjusting settings, a process that can take days and simply doesn't scale once a quantum computer grows to have thousands or eventually millions of qubits. Trying to manually calibrate a system that large would be like asking one orchestra conductor to individually retune 1 million instruments by hand every single day, forever. Nvidia's answer is called Ising calibration, a vision language model, meaning an AI that can look at raw measurement data streaming out of a quantum processor and instantly understand what it's seeing, the same basic skill that lets modern AI models interpret photographs or read documents. Except here, instead of identifying a cat in a picture, it's identifying exactly which qubits are drifting out of tune and automatically correcting them continuously without needing a human physicist to sit there watching a screen. According to Nvidia, this model has already outperformed some of the most advanced. That comparison is worth pausing on for a second because it's a genuinely unusual claim. Nvidia reports that its purpose-built calibration model outperforms some of the most capable general-purpose AI language models currently available, systems trained on enormous amounts of general knowledge, on this narrow, highly specialized quantum calibration task. It's a reminder that bigger, more general AI isn't always the better 2L for every job. Sometimes a smaller model, trained specifically and deeply on one narrow problem, can outperform a much larger, more famous system that was never built with that specific problem in mind in the first place. Then there's the second half of the problem, error correction decoding itself, arguably the harder and more urgent challenge of the two. This is the part of the system responsible for actually catching and fixing errors in real time, before they corrupt a calculation beyond repair. Nvidia's solution here is called Ising Decoding, built using a specific kind of neural network architecture borrowed from computer vision technology, the same underlying approach used to help self-driving cars recognize objects around them in real time. According to Nvidia, these decoding models deliver up to 2.5 times faster performance and 3 times higher accuracy compared to the previous industry standard decoding software. Sit with those numbers for a second, because they're not just incremental improvements. In a field where speed is measured in millionths of a second, and where errors compound rapidly the larger a system gets, doubling and tripling performance. This isn't just convenient, it's the difference between a quantum computer. There's also a practical engineering detail here that matters more than it might initially sound like it should. Nvidia actually built 2 separate versions of the decoding model, one specifically optimized for raw speed, and another optimized instead for maximum accuracy. That choice reflects a real trade-off engineers constantly have to navigate in this field. Sometimes a slightly less accurate decision made instantly is more valuable than a perfect decision made too late. Other times, especially for particularly delicate or high-stakes calculations, accuracy matters enough H that it's worth accepting a small amount of extra delay. Giving engineers the choice between these 2 priorities, rather than forcing one single compromise onto every possible use case, is exactly the kind of flexibility a maturing industry actually needs. Jensen Huang, Nvidia's CEO, framed the significance of this shift in a way that's worth sitting with. According to Huang, artificial intelligence has now become essential to making quantum computing genuinely practical, with AI effectively becoming the control system, the operating system, run NDG underneath the entire machine, transforming a collection of fragile, unreliable qubits into something closer to a scalable, dependable quantum GPU hybrid system. Coming from the CEO of a company whose own products are largely responsible for the current AI boom, that framing carries some extra weight. Huang isn't describing AI as merely a helpful add-on feature bolted onto quantum computing from the outside. He's in the same way an operating system quietly runs underneath every application on an ordinary laptop or phone, mostly invisible, rarely discussed, but absolutely essential to everything happening on top of it. And that phrase, quantum GPU hybrid system, is really the heart of everything happening here, and it's worth slowing down on, because it quietly redefines what a quantum computer even is. For years, the public imagination has pictured quantum computers as standalone machines, entirely separate from the ordinary computers we use every day, operating according to their own mysterious rules in some sealed-off corner of a laboratory. Nvidia's approach suggests that picture was always incomplete. A quantum computer, in this emerging vision, isn't a lone machine at all. It's one half of a partnership, permanently paired with classical GPU supercomputers, working alongside it, constantly watching, correcting, and steering the quantum hardware in real time. Think of it less like a solo violinist performing alone on a stage, and more like a violinist playing alongside a full orchestra. where the orchestra is constantly invisibly adjusting the room's acoustics in real time, correcting for every echo and every stray vibration, so the violin's fragile, delicate sound survives the trip all the way to the back row without falling apart. Without that orchestra of correction working underneath it, the fragile solo performance never reaches the audience intact. To actually make that partnership work at a hardware level, Nvidia built something called NVQ-Link, which functions almost like a universal translator and connector between quantum processors, built by many different companies using many different underlying technologies, and Nvidia's own GPU supercomputers. Before NVQ-Link, connecting a quantum processor to the kind of fast, powerful classical computing it needed for real-time error correction was a messy, custom-built headache, different for every single quantum hardware company with no shared standard tying it all together. NVQ-Link changes that by giving the entire industry a shared open connection point, allowing quantum processors of wildly different designs, whether they use superconducting circuits, trapped ions, neutral atoms, or photons, to plug into the same high-speed GPU infrastructure using a common architecture. It's the difference between every device in the world needing its own uniquely shaped charging cable versus everyone finally agreeing on one universal plug that just works everywhere, for everyone. That kind of shared standard matters enormously in a field this technically fragmented. Unlike classical computing, where nearly every major processor eventually converged around a handful of shared architectural principles, quantum computing today looks more like the wild early days of an entirely new technology, with several fundamentally different physical approaches all competing simultaneously, each with genuine advantages and genuine drawbacks, and no clear consensus yet about which one will ultimately dominate. Building a connection layer flexible enough to work across all of those competing approaches at once isn't just a convenience. It's arguably one of the few pieces of infrastructure the entire fractured industry actually needed someone to build. And this isn't some abstract concept still sitting on a whiteboard somewhere. According to Nvidia, NVQ-Link already has contributions and support from 17 different quantum hardware builders and 9 major scientific research laboratories, an unusually broad coalition for a technology industry that has historically been fiercely competitive and famously resistant to shared standards. When rival companies building fundamentally different quantum hardware start agreeing to plug into the same underlying infrastructure, that's usually a sign the infrastructure itself has become too valuable to compete against. The adoption numbers here are worth sitting with for a moment too, because they tell you this isn't just a flashy announcement sitting in a press release quietly gathering dust. Ising calibration is already being used by companies and institutions including Atom Computing, IonQ, IQM Quantum Computers, Inflection, QCTRL, and Academia Sinica, alongside major research institutions like Harvard's John A. Paulson School of Engineering and Applied Sciences and the Fermi National Accelerator Laboratory. Ising Decoding, meanwhile, has already been deployed at Cornell University, Sandia, National Laboratories, the University of California, San Diego, and UC Santa Barbara, among others. That's a genuinely broad cross-section of the field, spanning private startups building novel quantum hardware, elite research universities pushing the theoretical boundaries of the science, and national laboratories operating some of the most sensitive, well-funded quantum research programs in the entire country. It's rare for a single piece of infrastructure to earn buy-in from that many different types of institutions, with that many different priorities and incentives within the same handful of months following its initial release. That list matters because it spans the entire spectrum of the quantum computing world. Small specialized startups, massive research universities, and national government laboratories, all independently deciding this particular AI infrastructure was worth building around. When that many genuinely different organizations converge on the same underlying tool within the same few months, it's rarely a coincidence. It's usually a sign that a tool has quietly become closer to a necessity than an option. There's a smaller, quieter story unfolding alongside all of this too, one that shows exactly how this technology is already rippling outward through the wider quantum industry. A company called Quantum X Labs recently ran its own experimental error correction decoder on an Nvidia GPU, benchmarking a custom AI model against the older, classical, decoding method that had been the industry standard for years. In their tests, the AI-based decoder outperformed the older classical approach across multiple simulated error conditions, echoing exactly the kind of performance gains Nvidia itself has been reporting at a much larger scale. That's a small example, but it illustrates something important about how this technology actually spreads through an entire industry. Nvidia didn't just build a private tool locked away for its own internal use. It released Ising as an open source model family, meaning any research team, any startup, anywhere in the world can take that underlying technology, adapt it, retrain it on their own specific quantum hardware, and build on top of it. That's a fundamentally different strategy than simply selling a finished, closed product, and it's one Nvidia has quietly perfected before in a completely different industry. Releasing something this valuable as open source might seem, on the surface, like an unusual business decision. Why would a company hand over technology this powerful, essentially for free, rather than keeping it locked behind an expensive paywall? But this is a strategy Nvidia has run before, and run extremely well. By making the tools open and widely accessible, Nvidia doesn't just help other companies build better quantum systems out of generosity. It ensures that as those systems scale up and eventually need more computing power, Nvidia's own GPUs are already the default, deeply embedded choice sitting underneath nearly everything, because the entire surrounding software ecosystem was built around them from the very beginning. If any of this feels oddly familiar, that's because it is. Rewind a decade, and Nvidia wasn't the dominant force in artificial intelligence that it is today either. It made graphics chips, mostly for gamers. What changed everything was a realization that the exact same chip architecture built for rendering video game graphics also happened to be extraordinarily good at the kind of massive parallel mathematical calculations artificial intelligence requires. Nvidia leaned into that overlap aggressively, building an entire software ecosystem around it, and by the time the rest of the world caught up to how important AI was becoming, Nvidia wasn't just a chip company anymore. It had quietly become the infrastructure the entire AI industry was already built on top of. Quantum computing appears to be walking down that exact same road right now, and Nvidia appears to know it. Instead of racing to build its own quantum processors, competing directly against companies like IBM, Google, and IonQ, Nvidia is doing something quieter and arguably far smarter, positioning its GPUs as the essential infrastructure every single one of those competing quantum approaches will eventually need anyway, regardless of which underlying quantum technology ultimately wins the race. It's a strategy built on a simple but powerful observation, one that's easy to miss if you're only paying attention to the flashiest quantum headlines. No matter which physical approach to building qubits eventually wins out, every single one of them still needs to solve the exact same underlying problems, keeping fragile quantum states stable long enough to be useful and correcting the inevitable errors fast enough to keep up with how quickly those states decay. Those problems don't belong to any one specific type of quantum hardware. They belong to the entire field as a whole, which means whoever solves them best has genuine influence over the entire industry, not just one narrow corner of it. That's a genuinely clever strategic position to be in. Nobody yet knows for certain which type of quantum hardware, superconducting circuits, trapped ions, neutral atoms, photonics, will ultimately prove the most successful path toward large-scale, genuinely useful quantum computing. Companies and governments are pouring enormous sums of money into all of these competing approaches simultaneously, and it could still be years before a clear winner emerges. But regardless of which approach eventually wins that race, nearly all of them are converging on the exact same underlying need: powerful classical AI computing sitting right alongside the quantum hardware, watching, correcting, and steering it in real time. By building the calibration and error correction layer that works across all of those different approaches at once, Nvidia doesn't need to bet on any single winner. It benefits no matter which quantum technology eventually pulls ahead, because whichever one wins will almost certainly still be running Nvidia's classical infrastructure underneath it the entire time. It's a strategy that turns quantum computing's biggest ongoing uncertainty — nobody knows which hardware approach will win — into a source of stability instead of risk. There's a financial dimension to this story too, one that helps explain why Nvidia is moving with this much urgency right now. Analyst estimates suggest the quantum computing market could surpass $11 billion by 2030, and that growth trajectory depends almost entirely on the industry actually solving exactly the kinds of engineering challenges Nvidia is now targeting directly, error correction and scalability chief among them. In other words, Nvidia isn't just releasing a nice technical tool as a side project, it's positioning itself to capture a meaningful share of an industry. Many analysts expect to grow dramatically over the coming years by making itself indispensable to solving the one problem standing between quantum computing's current experimental phase and genuine real-world usefulness. That $11 billion projection, while still relatively modest compared to some of the eye-watering figures thrown around in the broader AI industry, represents a market that's expected to grow substantially from where it stands today. And growth on that scale tends to attract exactly the kind of aggressive early positioning Nvidia is engaged in right now. Companies that manage to embed themselves as essential infrastructure early in a market's growth curve tend to capture an outsized share of the value created as that market eventually matures, a pattern that's played out again and again across the history of the technology industry, from early internet infrastructure to cloud computing to, most recently, the AI boom Nvidia itself helped fuel. It's worth pausing here to really appreciate just how unusual this moment is from a historical perspective. For most of quantum computing's existence, the field has been dominated almost entirely by physicists, working with highly specialized, custom-built hardware, solving deeply technical problems, using methods largely inaccessible to anyone outside a narrow academic specialty. Nvidia's approach quietly imports an entirely different discipline into that world, the same modern AI and machine learning techniques that have already transformed image recognition, language processing, and countless other fields over the past several years. This kind of cross-disciplinary shift has a way of quietly reshaping who actually gets to work on the cutting edge of a field. As AI-driven tools take over more of the deeply specialized physics work that used to require years of highly specific training, the barrier to entry for building and operating a quantum system starts to lower, at least somewhat, opening the door for a broader range of researchers, engineers, and companies to participate in an industry that used to feel almost impossibly exclusive. That kind of democratization doesn't happen instantly, but historically, it tends to accelerate progress across an entire field once it takes hold. That cross-pollination matters more than it might initially seem. Quantum error correction, at its core, is fundamentally a pattern recognition problem, trying to spot the subtle signature of an error hiding inside a flood of noisy measurement data, then reacting to it correctly and instantly. That happens to be exactly the kind of task modern AI models have become extraordinarily good at over the past several years, recognizing subtle patterns buried inside enormous amounts of noisy data, faster and more reliably than traditional rule-based algorithms ever could. So, in a strange way, quantum computing's biggest bottleneck and artificial intelligence's biggest recent strength turn out to be a nearly perfect match for each other, almost as if two completely separate technological revolutions, happening in parallel over the past decade, were quietly building toward the exact moment they'd need to merge together. That merger raises a genuinely fascinating question worth sitting with. If AI ends up becoming the permanent nervous system sitting underneath every future quantum computer, watching over every qubit, correcting every error, calibrating every measurement in real time, then the old idea of a quantum computer as some kind of separate exotic machine starts to dissolve entirely. What you're left with instead is a single hybrid system, part quantum, part classical, part artificial intelligence, all working together so tightly integrated that it stops making sense to talk about them as separate technologies at all. This shift also raises a much bigger question about what actually counts as quantum computing's core innovation going forward. For years, the public conversation has been almost entirely fixated on qubit counts. Whoever builds a chip with more qubits wins the headlines, wins the funding, wins the attention. But if AI-driven calibration and error correction end up being just as important, or arguably more important, to actually making a quantum computer useful, then the real competitive edge in this industry might shift quietly away from raw qubit counts and toward whoever builds the smartest, fastest, most reliable AI system, watching over those qubits instead. That reframing would represent a genuinely significant shift in how the entire industry measures progress. Investors, journalists, and casual observers have spent years treating qubit count almost like a scoreboard, a single simple number that supposedly tells you who's winning the race. But a chip with an enormous number of qubits that can't reliably correct its own errors is arguably less useful than a smaller, more modest system with an exceptionally strong error correction layer sitting underneath it. Raw qubit count, in other words, might be a far less meaningful measure of real progress than most public coverage has been treating it as. If that shift fully plays out, it would mean the company that ultimately dominates quantum computing might not be the one that builds the most impressive quantum chip at all. It might simply be the company that builds the smartest classical AI system sitting right next to it. And right now, Nvidia has a significant head start on exactly that piece of the puzzle, an advantage most of its competitors in the quantum hardware space simply don't have the resources or expertise to easily replicate. Before we go any further, if stories like this, the ones where a familiar company quietly repositions itself at the center of an entirely new technological frontier, are the kind of thing you want to keep seeing, go ahead and hit like and subscribe, because there's a lot more of this quietly unfolding right now than most headlines are giving credit for, and it's worth being one of the first to actually understand it. There's also a broader industry pattern worth recognizing here, one that stretches beyond just Nvidia and quantum computing specifically. Throughout the history of computing, the companies that ultimately win the biggest, most enduring advantages are rarely the ones racing hardest toward the flashiest headline feature. They're usually the ones quietly building the unglamorous infrastructure everyone else eventually depends on, whether that's early operating systems, cloud computing platforms, or now, potentially, the AI layer sitting underneath quantum hardware itself. And that pattern helps explain why so many competing quantum hardware companies, ones that would otherwise be fierce rivals racing against each other for funding, talent, and headlines, are all independently choosing to build on top of the exact same Nvidia infrastructure at the same time. None of them particularly wants to hand a potential rival that much influence over their own technology stack. But the alternative, trying to build an equally capable AI calibration and error correction system entirely from scratch, alone, with limited resources, is simply too costly and too risky for most of them to seriously consider right now. There's an important nuance worth adding here too, one that keeps this story grounded rather than overhyped. Nvidia becoming central to quantum computing's supporting infrastructure doesn't mean the underlying quantum hardware problem has been solved, or that fully fault-tolerant large-scale quantum computers are suddenly right around the corner. Building better qubits, ones that are naturally more stable and less error-prone in the first place, remains an enormously difficult physics and engineering challenge in its own right, one that AI alone can't simply erase. What NVIDIA's approach does is make the errors that inevitably still occur far easier and faster to catch and correct, buying the rest of the industry more breathing room to keep improving the underlying hardware itself. So where does this actually leave quantum computing as a field right now in the second half of 2026? Still early, still experimental, still years away from the kind of world-changing breakthroughs occasionally promised in flashy headlines, but also quietly, meaningfully more stable than it was even a year earlier, thanks in large part to an AI layer most casual observers outside the industry have barely even heard of yet. It also helps to remember just how quickly this specific corner of the industry has been moving month over month throughout 2026. Nvidia released the original Ising model family in April, expanded NVQ-Link's public availability by the middle of the year, and has continued rolling out updates and broader industry adoption in the months since, with more research institutions and quantum hardware companies announcing integration, seemingly every few weeks. That pace of iteration is unusually fast, even by the standards of the broader technology industry, and it suggests Nvidia views this as far more than a one-time announcement. It looks instead like the opening phase of a sustained long-term push to become permanently embedded in how quantum computing actually gets built. Maybe in a few years, this becomes common knowledge, folded quietly into the broader story of how quantum computing finally became genuinely useful instead of merely theoretically impressive. Or maybe most people never learn the name Ising at all, even as it quietly becomes one of the load-bearing pillars holding up an entire emerging industry from underneath. Either way, right now, today, inside laboratories and data centers most people will never see, GPUs originally built to render video games are quietly learning to keep some of the most fragile machines humanity has ever built from falling apart, one corrected error at a time. That's really the through line connecting everything in this story, an industry built to make video games run smoothly quietly, discovering one unexpected application at a time that the exact same underlying mathematics powering realistic graphics and powering large language models also happens to be exactly what quantum computing needed all along, sitting there unnoticed the entire time, waiting for someone to finally make the connection. And that raises one last question worth leaving you with. If the chips originally built to render video games ended up becoming the backbone of the entire AI revolution, and are now quietly becoming the backbone of quantum computing too, what other fields, still struggling with their own version of this exact same fragile, error-prone bottleneck, might be the next unexpected place NVIDIA's GPUs quietly show up next?